Welcome to class 4 of compiler construction. Today we're going to do a bunch of little tiny things where the overall goal is to go from the C language to X0 and actually be able to run and really compile our programs. So recall that the thing that we did last was the explicate control function, which took programs that are written in R, but in the the output of RCO, and turned those to C programs. So what we'll do today is we're gonna basically do the thing that converts C programs to X. Now to do that, one of the main things that we need to know is we need to know what variables there are in the C program. And so we're going to write a function that's called uncover locals. And the job of uncover locals is basically to take a program in C and then turn it into a program with C that knows the variables. And this is the point where we will first use that info field. So basically what's going to happen is that before, the info field will just be empty. And then after, the info field is going to be a set of variables. So for instance, it might be the set of variables, X, Y, Z, A, B, C, so on, something like that. All right. And it's quite straightforward, actually. Basically, what we're going to do is we're going to say that when you call uncover on a program with some info and some mapping from main to a T, because remember, the structure that's on the other side of a label is a T that stands for tail, is going to be equal to a program where we have info prime of main and T, where info prime equals the set x0 ... xn if T equals a sequence of set x0 to something ... set xn to something, and then some final answer. So basically all this is going to do is it's going to go through the C structure, the tail structure, which remember is either a sequence of a set or an argument, and just read off what all the variables are. It's just going to read off every single one of those and just stick them in a set. So it's a quite straightforward thing to do. Okay, now once we know what all of those are, now what we can do is we can write the select function. And select is going to be more interesting. So this stands for select instructions. And so what it's going to do is it's going to take C to X. However, it's going to be a version of X that has variables and breaks some rules. Now when I say break some rules, what I mean is that it's not going to obey all of the constraints of real x86 programs. In particular, and we'll talk about this later, but in more detail. But basically, real x86 programs, you can't. It's like if you're gonna move a constant into a, or actually no, here's an example. If you have a variable in memory and you want to move another variable that's memory into that one, then you can't do that. You have to take the variable that's in memory, move it into a register, and then move that register into the variable in memory. Basically, an individual instruction can only look at memory one time. It can't look at it twice. So that's a constraint. So we're not going to obey that. Okay. So when we call select and we give it a program that has, some info and a mapping from main to a tail, then what we're going to do is we're going to turn that into a program. This now is, of course, an X program with some info, and it's going to have a block. Remember, block is the structure that, it's going to have a mapping from main to block, where the block is going to have its own info, which is going to start off as empty. And then it's going to have a list of instructions, which will come from calling select on t. All right, now how do you select a t? So let me actually write that select underscore t. So select sub t will either be given a return of an a, in which case what we'll do is we'll return the following sequence of instructions. We'll return move q of select a on that a into RAX, and then after that we'll jump JMP to end. And then if we're given a sequence instead, that'll have an S and a T. And what we'll do there is we'll just do select on a statement, S, and then we'll just join that with calling select on the T. Okay, so when we return, we move the answer into RAX. If you remember from when you did assembly programming, the answer to a computation, to like a function call or whatever, always goes in RAX, so that's why we're doing that. And if you recall from our interpreter for X programs, we look at RAX when we return our final answer, so that's also why we return that. Okay, now, if we do select of S, there's only one kind of statement right now, there will be more in the future, is a set of an X and an E. And what we'll do there is we're going to call select E. Now, select E is going to take as an argument the destination to put its answer in. So in which case, what we're going to do is we're going to call select A on X and then give it E. So now select A, this is a function that we haven't written yet, but we'll see it shortly. Actually, let's do it right now. So select A will either be given a number, n, in which case we'll return a number n, or it's going to be given a variable v, in which case we'll return the variable v. See, it's really the same thing. Okay. Next, we'll have select E. And it's going to take as an argument the destination that it's going to stick the answer into. And then it'll either get an argument, all right, arg A, in which case what we're going to do is we're going to return a list of instructions, which is going to be move q, and we want to move select A of that A into the destination. Okay, if we don't get an argument, what we're going to get is a read. Okay, and if we read, what we'll do there is we're going to do call q. So call q is though you call a function, and we're going to call the function readInt. And then after we call it, its answer is going to be an RAX. So we're going to move q RAX into the destination. Or, and here let me move more space. There we go. Or we're going to have a negation of an argument, in which case what we're going to do is we're going to move Q, select A into the destination, and then we're going to call negate, it's called neg Q, on the destination. So the idea here is that we put the value into the destination, then we negate it. Because neg Q is an instruction that negates something and puts the answer in the same place. We need to move our thing into it. Finally, we could have an addition, in which case we'd have an add with an argument on the left and an argument on the right. And what we'll do here is we'll move one of them into the destination and then add the other one. So we'll move select a, we'll move the right one into the destination, and then we'll do add Q of select AL and the destination. Now, just a little comment on this. With addition, it doesn't matter whether we move the left one or the right one. But if in the future you implement subtraction or division or whatnot, it's going to matter, right? Because you want to make sure it's the right one. And I actually forget what order they go in. It might be that the destination is actually the thing that's on the left, not the thing that's on the right. And if it's the thing that's on the right, if it's the thing that's on the left, then you would want to do the opposite. You would want to move the left-hand side into the destination and then add them. And that's something that guide on x86 assembly that I recommended we'll talk about. Okay, so, but anyways, at this point, we've now converted a C program into an X program. But of course, it is an X program that has variables in it. And of course, the real X machine, can't have variables. So what do? Well, right now, the whole system that we have looks like this. We have our R programs, and we do uniquify on them, and we get new R programs. We do optimize on them, and we get a new R program. We do RCO on it, and we get a new R program. We do econ on that, and that gets us a C program. We do uncover, and that gets us a C program. We do select, and that gets us an X program. And now what we're going to do is we're going to do two more transformations on X. The first one is going to be called assign, and the next one is going to be called patch. So remember that this version of X has two constraints. The first is that it has variables, and the second is that it breaks some rules. Assign is going to make it so that it doesn't have variables, and patch is going to make it so it doesn't break those rules. So, assign homes, that's what's next. Assign homes. It'll take an X program with variables and return an X program without variables. Now, normally, this is going to be the place that we implement something called register allocation. Now, what register allocation does is it looks at your program, it sees, aha, you use these variables in these places and these variables in the other places. So what I'll do is I'll assign these ones to register 1 and these ones over here to register 2. And using registers is very efficient. The reason it's efficient is because the machine is basically optimized to make it so that registers are the fast place in memory, the fast part of the machine. They're not really even in memory. So they're like the lowest level of the cache hierarchy, or the highest, depending on how you want to look at it. But it's complicated to do that. What we want to do is we want to work fast and incrementally. So we're going to make a version of our compiler that doesn't use registers at all. Actually, it only uses RX. Because remember, we used RAX right here to store the return value. So it uses RAX, but it won't really use anything else. So here's the way it's going to work. We're going to make it so that every single variable, no matter what, lives on the stack. And since everything lives on the stack, it'll be easy to, store. It'll be easier to. Sorry, I would say this. It'll be easy to know how to get rid of variables in the X program, because we'll just put them in stack locations, which are just places in memory. Okay, so that's the plan. So what we're going to do then is all we have to do is count how many variables there are and know that we need that much stack space. So basically, assign is going to take a program that has some info, which is just the set of variables that it uses, x0 through xn. And actually, let's call it x1 through xn, just so that I won't have an off by one error, because we're gonna look at the total number of them. Okay, so we have these variables, and then we have our main function, which is a mapping to a block that has no info there, and then it has its instructions, which we'll call is. All right, so that's what assign is given. And what we're going to do is we're going to produce a new X program. In this new X program, it's going to need to know how many variables there are and how much space we need. So the number of variables, how many variables, that's n. This n right here is how many there are. And then we also need to know the stack space. And the stack space is easy. It's just 8 times the number of variables. Now, here's kind of a little annoyance. Turns out that on modern machines, the stack has to be aligned to 16 bytes. Why does it need to do this? Basically, the reason it needs to do this, how's the best way to explain this? If you do a system call, then what that does is it causes an interrupt to happen on your machine, which escapes from whatever the local user code is and goes into the kernel. And then when it goes into the kernel needs to save the state of your program so that it can go back to it after it handles whatever the system call is. Now, when it saves the state of your program, it needs to dump the contents of every register somewhere. And the place that it does that is it does it onto the stack. Now, when it dumps the contents of registers, one of the registers that it needs to do are the vector registers that store SIMD values. And those ones can only be read or exported to addresses that are divisible by 16. Now, why do they do that? It's because that's how big they are. They are, they're, what is that, 256? I guess they're 256 bits. And so since they're 256 bits, they can't be stored in places that don't align with 256 bits. So, because when you call a function, it might need to call a system call. That system call needs to be able to dump the registers, which means that when you call a function, the stack has to be aligned to 16 in case it needs to do it. So that means that when you modify the stack, you need to make sure that you modify it in these 16 value increments. So basically what that means is that we either need to do n or n plus 1, depending on whether n is even or odd. If n is even, then we can use it because it's going to be divisible by 16. Because either if it's even, right, then it was 0, which means that it was already divisible by 16. Or if it's like 4, well then 4 is divisible by 16. 4 times 8 is. But if n was odd, then that means that we need to add 1 to it and use a little bit extra space. Okay, so we need to know how much stack space we're going to use. Okay. So then what we're going to do is we are going to return a new program. We're going to return a new program. And this new program is going to use the stack space, is going to acquire the stack space, um, and then um, actually, run whatever our program is. So here's the way it's going to look. We don't need to keep track of any info anymore. Maybe if you wanted, you could keep track of what the stack space is or something like that, but you don't really need to. Okay, then it's going to have a bunch of blocks. It's going to have one block that we're going to call main. And in the main block, what we're going to do is that we're going to push Q the RBP. Then we're going to move Q our SP into our BP. Then we're going to subtract. The stack space, so SS for stack space, from RSP. Then we're going to jump to the body. Okay, so what's going on here? When you make a function call, there are two values that are relevant. There's the stack pointer, which is the current place of the stack, and then there's what's called the stack base pointer. Basically, the base pointer is the previous place where the stack was on the previous stack frame. So all of the local variables are relative to the base pointer, not relative to the stack, because the stack keeps going down. So basically, by pushing the base pointer, what we're doing is we're saving the previous function call's base pointer, because we're going to overwrite it. Then what we're going to do is we're going to take the current stack pointer, so the current stack pointer, and move it into the base pointer, because when we got the stack, when we acquired the stack, that location is our base pointer. Okay, so we're going to push the base pointer to save it. Then we're going to move the stack pointer onto the we're going to move the new location of the stack pointer into the base pointer. Then what we're going to do is we're going to subtract SS from the stack pointer. So what that means is that we're going to move the stack down the amount of space that we need. So that means that there's now this gap in the stack. That gap in the stack are where all our variables are going to go. Then we're going to jump to the body. At the end of our program, and I'm writing end here, and this end, by the way, is the same end that we jumped to on our return. What we do is we are going to add Q SS to RSP. This is giving back the space on the stack. Then we're going to pop Q into RBP, which is going to give back more space, and it's going to restore the previous base pointer, and then we're going to return. Basically what goes on here is that these steps are the opposite of one another. We go into the body, and then we come back to end. We subtract, and then we add. We replace the base pointer. We save the base pointer and then replace it versus restoring it. We were called, and then now we return. So main is what happens at the beginning of a function, end is what happens at the end, and it restores the state of the stack exactly as it was before. In the future, when we actually use registers, in these little pieces of code, we're also going to do stuff like save callee saves registers, for instance. Okay, then what we're going to do is now we're going to change the body. And the body is going to be, we're just going to call a function that's going to be called assign, and we're going to give it a renaming environment row, and we're going to call it with the instruction list. And what row is is a mapping of xn, or actually I'll write it as xi, is going to go to RSP, or RBP, 8 times I. Okay, now what's going on here? So remember, RBP is the new base pointer. That's the start of all our stack locations, the start of all the places that we're allowed to look at. And so what we do is we say that variable 1 is the first thing after that. Variable 2 is the second thing after that. Variable 3 is the third thing after that, and so on. I guess we might need to subtract 1 from I because I said that the variables were ordered, you know what I mean? But you'll get it off by 1 error and then you'll fix it. By the way, why is it 8? Remember, it's 8 because we're assuming that all values are 64-bit, and 64 bits are 8 words because they're 8 bytes. All right, so now let's write this assign function that's actually going to go through and do the rearrangement of things. So we got 4, 4. Okay, so assign is a simple mapping. So if we assign row on the empty list, we get back the empty list. If we assign row on a one thing and then something else, then we just assign on the first thing and then assign on the rest. Okay, so it just maps over. Okay, but now let's talk about how we actually do it inside of the instructions. Well, if we do assign row on an add queue of an AL and an AR, then what we do is we do an add queue of assign row of AL and then assign row of AR. So it just walks across that too. It walks across all of them. So if we were given a neg queue of an argument, then we're going to do neg queue of assign row of that argument. It just walks across everything. Its whole job is to get down to the variables. When it gets down to the variables, if it sees a number, n, then it's invariant. It just leaves the number alone. But if it sees a variable v, then it looks up that variable inside of v. That's all it needs to do. So your program started by having variables everywhere, and now it's not going to have them. It's going to change them to offsets. Cool. Okay, so we're good there. And oh yeah, and if we already had a register, then that stays the same as well. It only changes variables. And so now, after assigns, there are no variables anymore. Our program contains only registers and offsets, and constant numbers, of course. All right. So now, what do we need to do next? So now we need to do that patch function. And the point of the patch function is that it is going to, it's going to make it so, we don't violate the rules of x86. And basically, the rules of x86 are that you can't have 2 references to memory in a single instruction. So patch, it takes an X program, it returns an X program, and it recurs through the structure just like assign does. All it cares about is it cares about instructions that have two arguments. So at the bottom, if we look at like how patch works on a list of instructions, it's going to be given a cons of an I, that's one instruction, 2 instructions, and what it's going to do is it's going to call patch of I on I, and then it's going to merge and it's going to append onto that what happens with patch is of is. Notice that this is a plus plus, not a cons, because what will happen is that patch can return multiple things. So what I mean by that is that when you call patch and you give it an add queue, and suppose that you gave it an add queue that has two offsets, which means that there's a register 1 and an offset 1, and another register 2 and an offset 2. In that case, what we need to do is we need to move, remember this is the source, and this is the destination, okay? So what we need to do is we need to leave the destination the same. So what we do is we move R101 into a temporary register, and then after that, then what we do is we do an add queue of the temporary register and R202. All right. Now, which temporary register do we use? Can we do RAX? We can't do RAX because we're already using RAX for the final result. So we have to choose. Oh, sorry, that's wrong. That's stupid. We can use RAX because the only thing that we use RAX for are like I said, are the return result. So we can use RAX here. So we're going to move this piece of memory into RAX and then add RAX in that thing. We need to do this for every instruction that could mention multiple things, so move queue can do that as well. In this case, what we do is we follow the exact same pattern. We first move queue the source into the temp register, and then we move queue the temp register into the destination. And so notice that one instruction has now become two instructions. That's why I need to do this append right here. And in all other cases, the instruction just gets passed through as just one thing. Okay, we now have patch. Basically, the only thing that we need left to do is we need to actually spit out the assembly code, right? So we previously wrote an emitter for X that can turn it into assembly code. But we also need to make it so that these calls to read that we did right here, call readInt, actually do something. And similarly, we need to be able to see the final answer, because the final answer is going to be a number, and we want to know what that number is. The code that's going to do that is called our runtime. So we're going to assume that we're going to make a function we're going to make a program that's called runtime.c. And this is literally a C program. I mean, obviously you can write this in anything you want, but I recommend writing it as a C program. And basically what it's going to do is it's going to be really simple. It'll just have a function that's called readInt that takes no arguments. And what it'll do is it'll define a variable x, and then it'll call scanf, and then it'll read in something in decimal and store it in x, and then it'll return x. Okay, so this is just a really simple read function. Then we'll have another function that's called printInt. And what it's going to do is it's going to call printf of d, and then it's going to just print out whatever. Oh, sorry, and it has an argument int x, and it'll print that out. And then it'll return 0. Okay, in this runtime, what we'll do is we'll make our last final thing, which is going to be called main, which is going to be an x to x function. And what it's going to do is it is going to generate the wrapper around our code. Actually, you know what? I called this main right here, but really I should have called it begin. So I'm replacing that with begin. Okay, so what main is going to do is it gets a program that has some blocks. And what it's going to do is it's going to return a new program with the same blocks, except one more. And this new block will be a binding for main. And I'm writing underscore main because I'm assuming that you're on a machine that requires them to have an underscore in front. That's not necessarily the case for the machine that you're doing. You might not have an underscore underneath them. And what it's going to do is it's going to be a block with no info, where what it's going to do is we're going to do a call queue of begin. That's that, that's the code that we generated right here. We're calling this thing right here, we're calling this begin. So we're calling that begin. Then that's going to come back with an answer in RAX. So what we're going to do is we're going to move queue RAX into, I believe it's RDI. And then we're going to call queue of printent. And then we're going to return queue. The reason we're doing this is that begin is going to compute a number, and then we want to see it. And when you call functions, their arguments, the first one comes in RDI. All right. So now, what's next? How do we attach this and make it all really work? What you're going to do is in the bowels of your program, you have a step that looks at an X program and interprets it and makes sure that the answer for that X program is the same as the previous version of the program. Well, what you'll do is you'll expand that out. So you'll make it so that I'm gonna imagine that I'm gonna call this test on real hardware. Okay? And this is going to be a function that takes an X program and returns a number. This test on real hardware is the equivalent of the interpreter, but it's going to use the actual machine that you're on. And here's what it's going to work. Here's what it's going to do. It's going to do write, emit the X program into, I'm going to call it x.s. X because that's the language we're doing, and .s is the traditional extension for assembly programs. Then I'm going to execute cc, that's a C compiler, runtime.c, that's my runtime, x.s, and then I'm going to output x.bin. Then what I'm going to do is I'm going to execute x.bin, and I'm going to put the answer in answer. And that's answer as a string. Then what I'm going to do is I'm going to do, let answer equals string to number on the answer as a string. And then I'm going to return the answer. Now I have a way of taking an X program and turning it into an actual honest-to-goodness number. Because I emit it as an assembly program, I compile the assembly program using using the C compiler to compile the runtime, and the C compiler it knows how to see an assembly program, with .s, and assemble it, and then that gets me a binary. Take that binary and then run it, and then I just look at the output, and I save the output, and then when I look at the output, now I have a number as a string, and then I turn that string into the real number, and then look at it. Now, if you do all of this, you are at step 50 of the class project. Now, just so you kind of get it, that step 50, I expect you to do roughly like, you know, like a third or like halfway through the class. And even though we've only had 4 days of class, um, you know, this is kind of a lot of programming to get to this point. But I hope that this discussion of laying out what all the steps are helps you see that it's kind of an incremental process where you can test each one by comparing the related interpreters with one another. And at this point, we now have a real, actual compiler that does something real. It takes arithmetic expressions that have variables and turns them into x86 assembly programs. Now, obviously, it can only do negation and addition, but I hope that as you're looking at it, you see that it's almost like just a mere labor of engineering to make it have, multiplication and subtraction and other kinds of values like that. The hard part of this compiler is the structure, knowing how the structure should work and how everything connects together, not the details of knowing that, an add in the program becomes an add queue instruction. That's kind of the boring part. All right, now what we're going to do next time is we are going to start doing real register allocation. Now, when I say real register allocation, what I mean by that is that this program is like a bad compiler in that all of the variables are all stored in just on the stack. And so we're not making use of the fast memory that the machine has available. And so what we'll do next is figure out how to actually do that. All right, see you next time.